All right, so we are continuing with transformers today, and we'll hopefully get into GANs. So last class, we covered up pretty much everything else as far as architectural details for how transformers worked. We ended with a demo looking at the dimensions of transformers. So to start off today, we are going to go into that demo, but a little more in depth. All right, so if you remember, we had an encoder and a decoder. And if you remember, we fed different sized inputs into into the encoder and decoder respectively. You remember the dimension of the input to our encoder. I heard L by D. We're going to subscript that L with the number 1 because there are multiple L's in the transformer architecture. Okay, L1 by D for the encoder input. What about for the decoder input? L2 by D, exactly. And so an example of L1, if we're doing language translation and we're going from I am a student to je suis estudiant, we would, oh, and actually we made it L2 plus 1 by D, because if you remember, we also include a start token for the decoder. So yeah, L1 would, in this case, would be for I am a student, and then L2 would be 3, je suis étudiant, plus 1 for the start token. Any questions on that? Yeah. Can you input an end token? Yeah, but the network will probably not know what to do with it because during training, it will never see end tokens. So the input to the decoder, if you remember, is your targets shifted left on the encoder side. So the encoder takes as input our English sentence with no start or end tokens. Yep. Okay. And then what is the output dimension for our encoder? Remember, this is our special property of transformers, right? Of self-attention is that it preserves the sequence length dimension. And so our output dimension will be L1 by D. Then the output of our decoder will be 1 plus L2 by D. But in this case, our targets are shifted right. So we will be predicting J for the first token and then end for the last token. Okay, so now we're going to look inside. So inside this, we are going to have start with splitting our input into 3 copies. And each of those copies will be the same size as the input. And we are going to do a single head attention example. If we were doing a multi-head attention, then you can just imagine that these linear layers right here would be, we would take the output of them and we would split them into, for example, 8 different outputs and perform attention on each of them. In this case, though, we're only doing single head attention. And we will call the output of this first linear layer, Q, the output of the second linear layer, K, and the output of this third linear layer, V. So do you remember the first operation in our attention block is going to be between 2 of these matrices, Q, K, and V. Do you remember which 2 we will multiply together first? Q and K. That is correct. And we can call the output of that our attention matrix, or A. And so, quick question, what is the size of Q? What are the dimensions of Q? Someone I haven't heard from yet. Dimensions of Q. What is the relationship between Q and our input? It's a single linear, it's not a copy, but good thought. But it's a linear transformation of the copy, right? Or a linear layer away from it. And so, yeah, we will say, because we're doing single head attention, that the output dimension of that linear layer is D. And so the dimension of Q will be L1 by D. Same thing with K, same thing with V. So then, does anyone remember what the size of our attention matrix would be then? Yeah, Drake. L1 by L1, exactly. And that's because we're multiplying Q by K transpose. And yeah, Drake, how would you intuitively interpret that attention matrix? Actually, let me hand you the mic.
Well, it would appear that each element in the matrix corresponds to a pair of 2 elements in the input, right? And so I guess it tells you like how much element, say A, should pay attention to element B in the matrix.
Yeah, exactly. And so we have this, you can call it a similarity matrix or attention matrix, telling us the compatibility of each pair of items in the input. And how are we going to use that compatibility matrix or that attention matrix? Yeah. We are going to multiply it by V to get probability scores for the values, exactly. And so, yeah, and so in fact, so actually we are going to interpret A as our probability scores and use those probability scores as a weighted combination and take a weighted linear combination of V with those probabilities. Yeah, and so in here, before we multiply by V, I'm just going to write SM for softmax. And that normalizes our attention matrix to probabilities. as well as providing an activation function, a nonlinearity. And so then V is L1 by D. So then what will the output of our A of multiplying A by V be? We're taking L1 by L1, multiplying that by an L1 by D, and we will get out L1 by D exactly. Okay, and then we also have a concatenation step across the multiple heads of attention, followed by a linear layer here. But those, because we only have a single head, it will be D, or those will preserve the dimensionality of what we already have. If we were to have multi-head attention, just a note, V would be L1 by D over 8, and then the output of this would also be L1 by D over 8. And then when we concatenate all of those together, they would become L1 by D. Is that any questions on how this would be different from multi-head attention? Okay. Yes, for Q and K as well. Yeah, so Q, K, and V would all have would be L1 by D over 8 for multi-head attention. And then we would, and same with our output right here, would be L1 by D over 8. And then when we concatenate, they would become L1 by D once more. Okay, so then those go through a linear layer, which we will, well, yeah, represent as a box, and then get passed out of our encoder. Okay, let's look at our any questions on the encoder before we move on to the decoder? Yeah, Sophie. Oh, where does the 8 come from? Yeah, I'm sorry. So unfortunately, I'm not getting onto the internet on my tablet, which would make it easier to draw. But the over 8 is when we have multiple heads of attention. So basically, this allows the attention to look in multiple places. And so what we would do is when we would take the output of Q, K, and V, and then that would be a vector of length D, well, L1 by D. And then we would chunk that up into 8 chunks. 8 heads, yep. No, it's a hyperparameter, so you can pick how many heads you have, but 8 is a common choice. Yep, D over N, where N is the number of heads. Exactly, you got it. Yep. All right, so let's look into the decoder. We again, I guess, does anyone remember the main blocks that we have in our decoder off the top of your head? Yeah. Exactly. Yeah. So I guess the first question is, how many attention blocks are there in the decoder? I'm hearing 2. That is correct. Yeah. So there will be one self-attention block and then one cross-attention block, which is what you were talking about, where we look at the encoder. So let's look at the self-attention block first. So again, we have Q, K, and V. And those will have the same shapes respectively as in the encoder. And We will multiply Q and K together, get our attention matrix, and multiply that by V. You get the output. Oh, actually, we're missing a step. The step that is different. So we multiply Q and K together to get our attention matrix. But at this point, we apply an attention mask. And what does anyone remember what the attention mask does? Yeah. Exactly, yes. The mask prevents each word from looking at the word after it. So if you remember, our decoder, we have to be very careful with how we structure our decoder because all of the answers are provided as inputs to the decoder. And so in order to prevent the network from looking ahead and seeing the correct answer, we apply this mask. And however, the mask does allow you to look backwards and see the things that came before you. And so what this mask looks like is a upper triangular matrix. So it's a square matrix, just like the attention matrix is, with ones above the diagonal, allowing, yeah. And then this mask is the same size as the attention matrix and is multiplied by the attention matrix, zeroing out all attention values between each token and the tokens that it's not allowed to see. Any questions on how that mask works? Yeah. The mask, yes, is an upper triangular matrix. Okay, and so all of these dimensions are the same. And then we multiply this by V and get an output of size L2 by D, or L2 plus 1 by D. Okay, I'm about to erase this because we need to make space for the cross attention. Any questions on this? Yeah, Sophie. Good question. So let's see if you can answer that question. So the question is whether the mask will be a different size at each step. Yeah, so first let's make sure we know what we're talking about. So are we talking about inference or training? Let's talk about each of these cases individually because the answer is different, right? Okay, so during training, we pass the entire sentence into the decoder, right? And the mask makes it so that things can't look ahead. And so when you're talking about the input size changing, it does not change during training. And this is the difference between RNNs and transformers. Remember, transformers, you had to get a prediction, or for RNNs, you had to get a prediction because you needed that hidden state. And then you would feed that prediction, feed in that new hidden state along with the next token. And then you would have that sequential step process during training. In transformers, we get rid of that recurrence dependence. That gets rid of the sideways arrow in the recurrent neural network. And so because of that, we're basically passing in an entire block of hidden states. And the mask just determines which of those can pay attention to each other. And so that's how basically the mask substitutes for the directional arrow in the RNN. So I am a student was the input to the encoder, right? Yeah, exactly. Yeah. Yeah, so so to clarify, first of all, is there a mask in the encoder? Nope, you're right. Yeah, so there's no mask in the encoder. So I am a student can see I am a student. All of those words can see each other because they're not part of the prediction task. But je suis étudiant should not see the future words because they are part of the training task. So they can see the past words. So étudiant can see je suis. Exactly. Yeah, it's je suis étudiant versus itself. Yep, exactly. Yeah, let's talk about inference. So at inference time, is there an attention mask in the decoder? To be honest, I'm not sure like the actual implementation details, but effectively there isn't actually. Because at prediction time, we have none of that future information even given, right? Exactly. So there's no real effective mask in the decoder at inference time. Because we want them to be able to see everything that was generated before themselves, but we're not risking any potential information leakage because we don't have the target provided as input already. Okay. Hopefully that was helpful. I mean, I'm sure you're not the only person that has that question. It is always a nuanced question. Like, are we talking about training versus inference, and how do these different things work? So, yeah, I think that was a good discussion. You had a question? Yes. So at inference time in the decoder, do we have a QKV? Yes. So the first pass through at inference time, what would be the dimension of the input to the decoder? For the first step of the decoder inference, what would be the input? This is not a rhetorical question. Yeah, what do you think? 1 by L2 by D? Oh, 1 plus L2 by D? Yeah. And what would L2 be at the beginning of inference? It would be 0 because we don't know what's coming in. And so what would that 1 correspond to? The start token. Exactly. So first step at inference, we pass the start token in, get a prediction. And let's say we're just using greedy decoding. So same things apply to transformers that apply to RNN. We can do greedy, beam search, sampling as decoding options. Let's just say we're doing greedy. So we take the argmax token and pass that in with our start token to the decoder for the second. So now what is the size of our input to our decoder at step 2? Okay, let's see from the back, my back left corner of the room. What is the size of the input to the decoder in step 2 of inference? Yeah. It would be 2 by D. Yeah, and what would the first item be? The start token. And the next one would be the prediction for the first output. Exactly. Yep. And so at that point, our attention mask, well, yeah, at that point, basically our attention mask would only be masking, let's see. Yeah, so yeah, effectively there's no attention mask at inference time. And so yeah, we start and we just build up that sequence length as we make predictions. Yeah, question. So when you say change the decoder, we're not changing any of the weights, right? We're only changing the inputs. But yeah, we're not changing the inputs to the encoder. We are changing the inputs to the decoder. And yes, also when I say there's no effective attention mask, there is an attention mask which prevents the start token from seeing the word J at inference. However, we're predicting at inference, we're only taking the last token prediction. And so it doesn't really, that's what I mean by the attention mask doesn't matter, is it doesn't matter that start is masked because we're only taking predictions on the last token. Okay, well, let's look at cross attention. So we're going to erase this and replace it with just a single module because we know that the self-attention step preserves the dimension. So we are replacing what we just had with a layer that we've just named masked self-attention. And now you're going to take the output, and we want to have a final output of size 1 plus L2 by D. So if we look over here to the encoder, which dimension determined the output dimension of the, sorry, let me think about this for a second. Okay, I want to make sure I'm not leading you astray, so I'm going to look something up quick. Because this cross attention is a bit nuanced. Okay, yeah, so the question is, which of the dimensions of Q, K, and V determined the dimension of our output of the encoder? V? I do not think so. I believe the answer is Q. Because if you remember this first L1 came from Q, the second L1 came from K, and this third L1 came from V. And the second and third L1s canceled each other out when we multiplied the attention matrix by V. And so the output dimension was determined by U. And so we want an output dimension of 1 plus L2 by D for the decoder. And so we will take the output of our masked self-attention layer, and that will become U. And then K and V will come from our encoder. And this is cross attention that's happening right now. Exactly. And unfortunately, I'm crossing those lines, but this K and V on the right are coming from the encoder. So now this is kind of interesting. We have not the same shapes for each of these. So what's going to happen? So the first question is, what is the shape of Q? 1 plus L2 by D. And what is the shape of K? L1 by D, exactly. And so what will be the shape of our attention matrix in this case? L2 plus 1 by L1. Now think about that for a second and see if you can come up with how we might interpret that attention matrix. If it's L2 plus 1 by L1, what might be the interpretation of that? Yeah, what do you think? Yeah, how each token in the output corresponds to each token in the input. Exactly. Yep. And so then this is going, yeah. And so, yeah. And then if you were to try to guess why we would call this cross attention, how would you describe that? Like, why do you think we're calling this cross attention then? Yeah, no, it's good. Good. Yeah. So basically what happened in the first attention block of the decoder was that all of the output looked at all of the other output. In the second block of the decoder, all of the output looked at all of the input. And if you remember, we have skip connections in here as well. And so basically we're going to let our output look at the output, let our output look at the input, and then we're going to combine those by a skip connection. And so we will, our final output for each decoder layer will combine information from our output sequence as well as from our input sequence. Yeah, question. What was that? Yeah, great question. How do skip connections work here? So in the UNet, our skip connection came in the form of concatenation, right? In this case, our skip connections are simply come in the form of addition. So we'd add the output of the masked self-attention. Well, so let's finish up the dimensions here. So we take an L2 plus 1 by L1 and multiply that by an L1 by D and get an output of size 1 plus L2 by D. Exactly. And so that, if you remember, that was the exact same dimensions that we had for the output of our masked self-attention. And so because those shapes are the same, we can just add them directly to each other. And again, we will have a concatenation and a linear layer here, which we will just represent by this block. And we get an output of size L2 plus 1 by D. Now, this might have seemed like maybe a laborious exercise just to trace all these dimensions in the transformer, but if you can understand the dimensions of the transformer, you can understand the intuition for the transformer. And that's really what we're going for, is for you to understand really the information flow, how each of the encoder tokens look at each other, how each of the decoder tokens look at each other, and then how the decoder tokens can look at the encoder tokens as well in this cross attention. Yeah, question, Joseph. Great question. So what Joseph has asked, why do we need to pass our Q through a linear layer if it just came from a linear layer? And that is a very good observation. And in fact, the short answer is that you don't necessarily need to. The long answer is that actually it has been shown that you can combine this cross attention layer with the self attention layer just by this mask no longer is a square mask. It's you can imagine like having no masking between a matrix with no masking between the encoder and the decoder, and then partial mask, a triangular mask with the decoder, and then just concatenate those together. So you can actually kind of think of these being merged into the same layer, in which case, yeah, there would be no additional transformation for Q. So yeah, that's that. Any questions on all these dimensions for the transformer architecture? Yeah. Yes, multi-headed applies to both encoding and decoding. We do the splitting of the vector and then the concatenation within the masked self-attention as well as in the cross-attention. Yeah. Why do we have the skip connections? Number one, it helps the loss surface be a lot smoother and gives our gradients more direct access to our weights. That's just an optimization. That's just helpful for optimization. And secondly, I think it allows, it basically allows you to have more direct connections between our loss function and features at different parts of the neural network, helping for combining features across scales of abstraction. I think that's the best way I can describe it. All right. So that is the transformer architecture. All right, so now we are going to, there's one part we've missed, and this is just the technicality of how do we do positional encoding. And this is how. The idea is we want to have a fixed dimensional feature that represents the position of a token in our sequence. So you can imagine a couple of ways you could do that. You could have just a simple integer representing the position in the encoding. In this case, they chose to make the positional encoding a sign function of the position. And this is what that looks like. So basically, the sign function gets higher and higher frequency as you go through the as you go deeper into the number of dimensions. And so so on the y-axis we have token position, and on the x-axis we have the dimension in the embedding. So we have the first token in our sequence basically gets 0, 1, 0, 1, 0, 1, 0, 1 added respectively to each of the dimensions. The second token in our sequence gets 0, 1, 0, 1, but it's kind of annealed to be so that more sign periods happen within the number of dimensions. And as we go deeper, the oscillations of the sine wave become faster and faster. and that's how we represent position. Not the most intuitive thing. I wish we had the actual function on the slide, but we don't. But it's in the transformer paper. And so then we take this embedding, this position embedding, and we add that to the normal word embedding that corresponds to the token, and those combine, the positional embedding and the word embedding form the embedding that is the input to our network. Yeah. Exactly. Yeah. So the idea is that we just kind of provide information in the form of this sign pattern, and the transformer learns that represents position. Mm-hmm. Yeah. I think the easiest answer is that they found empirically that this worked well. I think also I'm not sure I have a great answer to you on that. It's not my particular field of expertise, but there's a lot of research that has been done on these positional encoding. So if you're interested, I'm sure you can find the answers you are looking for. Okay. So this is a note on the computational complexity of transformers. So this is comparing the computational complexity of self-attention, recurrent neural networks, and convolutional neural networks. So each of these columns represents something different. So I'll stand over here so you can see. So self-attention complexity per layer this is using big O notation for computational complexity, n squared times d. And this is where n is the sequence length. So this is kind of interesting. If you notice, the computational complexity of a recurrent neural network is only n by d squared. Any idea where that n squared might be coming from in the computational complexity of the transformer? You remember the dimensions of our attention matrix? They're L by L or N by N, right? And so that is a real actual limitation of transformers. So because of that L by L attention layer, there's no real good way to get around quadratic complexity with respect to sequence length. So that's, just a very important thing to be aware of for self-attention. Then D is the embedding dimension. Recurrent is n by d squared. Convolutional is k by n by d squared, where k is the number of filters. And then, sequential operations during training. Recurrent networks are uniquely bad because you have to pass the sequence into the network sequentially. So they require n sequential operations per training step. And then the maximum path length between the loss and your output, or between the loss in each layer in transformers, is 1 because of our skip connections. In recurrent networks is n, and because you have to go through each token in order that the loss has to travel from each token all the way to the output. Then convolutional, it is log base k of n. So just some important things to be aware of on complexity. As far as the results, transformers do really, really well. So this is kind of the original transformer architecture, which was not robustly optimized, but you can see in this language translation benchmark, blue score is a metric for quality of translation. And there's a significant improvement between transformers and recurrent networks. And this is just a slide showing how those scores have continued to improve. as the transformer architecture has been refined. A couple of failure modes, although these come with an asterisk. I believe that these failure modes have been resolved in later versions of transformers, but yeah, certain tasks like repetition tasks or counting tasks are more difficult. But in general, yeah, transformers tend to perform very well on language tasks. And that is where we will end for today.